This is the pre-video for section 2.4 so that you can get an idea about complex numbers before we come to class on Wednesday. Complex numbers are the solutions to equations that were not able to be solved before. Mainly, the thing that pops up is square roots of negative numbers. That's the big thing that's been a stumbling block for us so far this semester in terms of what we couldn't solve. So this is illustrating different types of solutions using the square root method. If you have x squared equals 9 and you take the square root of both sides, you get a plus or minus 3. Those are considered integers. If you have a fraction on the other side, notice both of them are perfect squares. You take the square root, you get two fractional answers or two rational numbers. If you have something that's not a perfect square, you get something called an irrational solution. And then we get this last case where x squared is equal to negative 9, which yes, 9 is a perfect square, but the negative throws us off. So this brings up the idea of complex numbers. Now, I always like to do a little side discussion here about the chart that I always teach when I first teach like 023 and 100, and we talk about the number systems. So before there were integers, because integers are things like 3 and negative 3, below that we had whole numbers, which is where you have like 0, 1, 2, 3, ... And we had the natural numbers, which was just 1, 2, 3, because when you first learn to count, you don't understand 0. Integers include now negatives of those and everything else. And then it goes on forever. From the integers, we go up and we hit the rationals. Rationals are anything that can be written as a ratio of A over B, and that can include terminating and repeating decimals, because those are all things that can be turned easily back into fractions. From there, on the other side, we have the irrationals, who are not related to any of the family of the tree that we've created so far. These are things like square root of 3 and pi. Those together make what we call our real number line, or our real numbers. Right above that, there's one more set that we're going to learn about called the complex numbers. The complex numbers contain everything from below, but they have a new element that will allow us to create lots of combinations. The square root of a negative 1 now is going to be something called I. So anytime we have a square root of a negative number, we can now talk about this new element or naming system. So here is the two main properties. These are the most used things in this section. You must be familiar with them. They are interchangeable in terms of if you see something that is going to represent one of these pieces, you must make the change. So anytime you see a negative under a square root, that is going to be pulled out as an I. Okay? Anytime you see I squared, you have to think of that as negative 1. Now these two relationships mean something. If you square both sides here, you get I squared equals negative 1. So the big thing is if I see the square root of negative 1, I know I have an I. If I see I squared, I know I have a negative 1. And then writing our answers in imaginary format, they're going to be written like this a lot. A plus BI, that is called the standard form for a complex number. This is its real part, and it has an imaginary part. So there's a chart on the next page that explains this a little bit better. A complex number is anything where you have A plus BI. So it could be just A, it could be just BI, it could be a combination of both. So notice 3 is just a real number, 2 plus I is a combination, and 2I is something we call a pure imaginary. Imaginary numbers have to have the I in them, otherwise they're not imaginary. Pure imaginary means it has the I and the number, it doesn't have the other piece. So it can't have that combination of a real and an imaginary to be a pure imaginary. And then there's some rules about sum and products. It's easier just to work through instead of trying to memorize some rules. So I'm going to just jump right down. You can read through some of those things if you want. It's just kind of textbook definitions. I'm going to go through example 1, which is how do I write my answer in the form A plus BI, where A is and B are real numbers, but this is the real part, this is the imaginary part, if we're either subtracting, multiplying, squaring, or doing some combinations. The nice thing about subtraction is it's essentially just like these were x's. I mean, you're just doing like terms. So you need to distribute that negative and then add like terms. Well, negative 3 and negative 2 added together would be negative 5, so that's my real part, and 8i minus 3i would be plus 5i. And that's as far as you can go because they're not like terms anymore. If you're trying to do multiplication, you can still use the distributive property. Just be careful because you're going to be multiplying with i's. So 8 times 7 is 56. 8 times negative 3i would be negative 24i. 2i times 7 would be 14i. And 2i times negative 3 would be negative 6i squared. Okay, let's talk about for a minute. We have this guy who showed up. Anytime you have an I squared, that means it's really a negative 1. So if I rewrite this, this is 56. I can combine these two I terms in the middle. That would be negative 10I. And this is now negative 6 times negative 1. So that makes that positive 6. So I still have one more step. 56 plus 6 is 62 minus my 10I. So there's my final answer there. This squaring one, you have to write it twice and FOIL, so it's very similar to part B. So 6 times 6 is 36. 6 times 7i would be 42i. 7i times 6 would be another 42i. 7i times 7i, and it's positive times positive, so that'd be positive 49i squared. But anytime we see an I squared, we know that it's really a negative 1. And not an I squared anymore. So this is actually 36 plus, that would be 84i, and this is now a negative 49. To finish it off, we need to do 36 minus 49, which is negative 13. So my final answer is a negative 13 plus an 84i. Okay, and this last one is a combination. This is like order of operations. We have to FOIL this first to get rid of our square, and then we'll distribute our negative and then combine like terms. So 3 minus 2i times 3 minus 2i. Bring down this. Okay, FOIL this. This would be 9 minus 6i minus 6i. Negative times negative would be positive 4, but then we get an I squared. Go ahead and distribute this. This would be negative 4 and plus I. Combining some like terms and going ahead and taking care of the fact that that is a negative 1. So notice this is negative 1 now, so that means that middle term is I guess it's a middle term, but that term right there is going to be a negative 4. So 9 minus 4 would be 5, minus 4 more would be 1. Negative 6i added together would be negative 12, plus 1 would be negative 11i. So essentially, this is not much different than stuff we did in section 1.3. The big key is that anytime an I squared pops up, you must change it to a negative 1. And then the last piece that we're going to do on the pre-video is the powers of I. This is an interesting concept. The pattern repeats every 4th degree. What we're going to show you what the pattern is that we're talking about. If you just do I to the first power, it's I. I squared, we know by definition, is negative 1. I cubed is when you break it down into something you already know, which is an I squared and an I to the first. I squared is negative 1. I to the first is I, so you get negative 1i or just negative I. I to the fourth is 2i squareds, so I squared times I squared, that's negative 1 times negative 1, which is positive 1. To show you what we mean by the pattern repeats, watch I to the fifth. That's an I squared times another I squared times an I to the first. We're using these two since they are facts. So I squared is negative 1, I squared is negative 1, I to the first is I. Negative 1 times negative 1 is 1, times I would just be I. So I to the fifth maps back to I to the first. And it keeps going. I to the sixth should then map to I squared. So let's prove that. So I squared times I squared times I squared. You'd need 3 of them to make 6. So that would be negative 1 times negative 1 times negative 1, which is negative 1. So notice I to the sixth is I squared. I like to draw this another way. I actually use a cycle chart. Made that too long. It just shows me that the cycle repeats every 4th. So this is I squared, which is negative 1. Down here would be I cubed, which is negative I, and I to the fourth, or yeah, fourth, which is positive 1, and then we're back to I. So if you have a small thing like I to the 13th, you could just count around the circle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I to the 13th is the same thing as I to the first. But not every time are you going to get small powers. In fact, if you look at my example, I have I to the 66. You don't want to count around that circle 66 times. So there's a trick. Step 1, make sure you have a positive exponent, because if you don't have a positive exponent, you can't use my trick. Step 2, divide exponent by 4, because the pattern repeats every fourth. Step 3, the remainder is your place in the cycle. So let me show what I mean by that. To the 66th. Okay, so that is a positive exponent. I'm going to divide it by 4 since I know my pattern repeats every fourth. 66 divided by 4, 6 goes one time. That would leave me with 26 come down. 4 goes into that 6 times. That would be a remainder of 2. That's the key thing there. So that means that this maps to I squared, and we know that I squared is negative 1. Now I could prove this by going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, blah, 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 blah. When you get here, this would be 62, because that is divisible by, well, actually, no, sorry. This is 60. So then this is 61, 62, 63, 64, 65, 66. So it does work out to be I squared. So it's a nifty little trick so you don't have to count around the circle. So I'm going to go ahead and do C part because it's also one that is positive exponent. Then we'll come back and talk about B. So if I do 4 into 92, 4 goes twice with a 12 coming, that goes evenly. So anytime it goes evenly, your remainder is 0. But that's just like saying that you're going to end up on the 4th power. So if you end up as something that goes evenly, you are always positive 1. But another way of thinking of that is I to the 0, which is the same thing as I to the 4th, and that is 1. Okay. And I to the 0 is a 0 power, so it's always a 1. This one's the tricky one. We have to turn this into a positive exponent, which means it goes in the denominator. So then we do 4 into 55. 4 goes one time with 1 left over, bring down the 5. 4 goes into 15 3 times with 3 left over. So this will reduce down to 1 over I cubed. But from our chart, we know that I cubed is an I squared and an I, so that's a negative I. Now you're not allowed to leave your answer like this because having an I in your denominator is the same thing as having a square root because I is the square root of negative 1. So the way to get rid of this is to remember that if you can turn it into an I squared, you can replace it with a negative 1. So this would be I over negative I squared. That's I over a negative times a negative 1 because this negative is not being squared there. So that would be I over positive 1 or just I. So a little bit trickier with the negative exponent. Okay, so that's the stopping point for the pre-video. Make sure you take notes on this so that you can use those for your daily worksheet on Wednesday, and I'll see you in class.